right, well, now that I kicked my noisy child out of the room, let's try this again. So talking about phase diagrams. And so phase diagrams, they're just a visual representation of the change between solid, liquid, gas, and so forth. And so any single point on these curves is just equilibrium between those phases. And so we need to talk about the important parts of a phase diagram. And so if we label it, we have to talk about how we have our triple point. That would be here. And this is just the point where all three states of matter coexist. We have our critical point. And this is where, I'll write that here. It's just indistinguishable between liquid and gas states. And so we call this line here, we call that our fusion curve. So remember when I talked about on the graph, the heating curve here, we had our delta H of fusion, which has to do with melting or freezing. Well, that's just this line here. And so we call this our fusion curve. And then we also have our, oops, I forgot to change colors, vaporization curve. Again, then on this portion, we had delta H of vaporization, and that is what this curve represents. Oops. And then don't forget also that this here, this is your sublimation curve. Because sublimation is the process between going from gas to solid. And so here's an example of a phase diagram for carbon dioxide. And so what's cool is you can, if it has actual labeled axes, you can pull data off. You can find out, okay, where does the triple point occur? Where does the critical point happen? Where does it have normal sublimation? Because remember, you're at 1 atm there. And so then we also can figure out density of phases. What's going to be more dense than the other? So we can get that from phase diagrams. So we'll talk about that here next. So what happens if you increase pressure on something? Well, the molecules get closer. And the substance becomes more dense. So if you're following a phase diagram along any line of increasing pressure and the substance changes forms, well, the form at the higher pressure will be denser than the form at the lower pressure. And so let's consider water, which I have to the right here. And so if we are going up this line, going from E to A to G, which is this line here, so we're increasing pressure across a line. What phase are we at in E? Well, that's gas. In A, we are in the solid phase. And lastly, we have G, and a wonderful typo here. I'll fix that before you guys get it. That is in the liquid phase. And so if we were to apply what I just told you here, that a substance at the higher pressure is going to be denser than the lower, does it make sense for water that the liquid form is denser than its solid? Yes. Because think about it. Does ice float on water? well, then water must be more dense. So this makes sense that you could deduce that the liquid form is denser than, then the denser form, man, I need more coffee, than the solid form of water. And then if we consider carbon dioxide, we are going to be following along this line here. Well, F then is in the gas phase, B is in the liquid, and H, another one of those typos, is in the solid phase. So now for carbon dioxide, in our case, its solid form is now denser than its liquid form. And so we can draw a conclusion from this, because there are subtle changes in these curves. Maybe you can spot that right away, but it has to do with the slope. So what we can say is that if the slope is positive for the solid liquid line, then it means that the solid is going to be denser than the liquid, which here in CO2 we have a positive slope and its solid was denser than its liquid. So if you have a negative slope like water, the opposite trend. That means the liquid's going to be denser than the solid.